Okay, so to continue our conversation about compound inequalities, I would like to talk about a few special cases. Now, last time we talked about some situations where if I gave you an inequality, so for instance, if I gave you something like x is greater than 0 and x is less than 2. Now, last time I didn't give it to you like that. I gave it to you that it looks something more like this. X is greater than 0 and x is less than 2. Now, be aware that these are exactly the same thing. And how would you graph that? Well, you would just simply put 0, put 2. X is greater than 0, so open circle. Less than 2, open circle, and everything in between. Now, that's not a special case. That's just a little reminder. So the special case would be something like this. What if I said x is greater than 0 and x is greater than 2? Well, what's so special about that? Well, it looks just like the one above, except for this time if I were to graph it, x is greater than 0 looks like this, and x is greater than 2 looks like this. A little bit different. This time the arrows are going in the same direction versus towards each other. Well, this is what I like to call an inefficient statement. Okay, x is greater than 0 and x is greater than 2. It's not a very good way to state what we're trying to say. We're looking for all the numbers that are bigger than 0 and bigger than 2. So one of the things that you need to think about here is the word and. The word and means inclusive. It means when we're looking at our graphs here, okay, we're looking for the area where both statements must be true. Okay, so let's think about that. What's a number that's bigger than 0 and bigger than 2? Number 1. Number 1's bigger than 0, but it's not bigger than 2. How about the number 3? Yes, that fits. Bigger than this and bigger than this. 4, 5, 6. All those numbers are that I just said. Well, if we look at our graph, okay, where are the numbers 3, 4, 5, 6? They're over here in this overlapping part. Okay, so when we are graphing something like this, okay, what we're looking for is we're looking for an overlap. And that overlapping part is what we want to draw. So we're actually going to draw a graph. I'll draw it down here. Okay, the way you would graph this is not like that, but instead you're going to graph just the overlapping part. So it actually would just be this. Also, this isn't a very efficient way to say this, so I'm going to rewrite this as the better way to say that is just to write x is greater than 2. Or if we use solution sets, all values of x such that x is greater than 2. This means exactly the same thing as this, except for this is a much more efficient way to state it. All right, so let's try another one. Let's see if that sank in at all. All right, so what if I wrote x is less than 4 and x is less than 8? Okay, tell me what that would be. How would you graph that? And if it's not an efficient statement, let's write it as a more efficient statement. Well, what I like to do, especially when I'm first learning how to do these, is I just graph them individually. So x is less than 4, x is less than 8. So we're looking for the numbers that are less than 4 and less than 8. Well, that's going to be all this region over here. So the actual graph for this will be this. Starts at 4 and works our way over. And the more efficient way to write it would be all values of x such that x is less than 4. Make sense? So you're looking for that overlapping part. Now, what if we threw an OR statement in there? Okay, what if I wrote x is less than 2 or x is less than 5? Okay, well here on this one, if I were to graph it, I'll graph it over here. 2, 5. Now what does the fact that it says or, how does that change it? Because if this was and, we'd be looking at this overlapping part. But or means all-inclusive. Okay, if you think about it, we're looking for a number that's bigger than 2 or bigger than 5. We don't really care as long as it's bigger than, or probably not bigger, less than. A number that's less than 2 or less than 5. We don't care if it's less than, just less than 5 and not less than 2. As long as it satisfies one of them, we're happy. Okay, so when I look at my graph, I'm going to use the part or the parts of the graph that covers everything. So if you think about this, we're going to use everything being shaded. So from here over. So my actual graph will look like this. Okay, it'll be at 5 and over. And a more efficient way to write it would be all values of x such that x is less than 5. Okay, so as we look at these things, those are two big parts right there. And on these special cases, you need to look for the overlapping part. Well, or we're just looking for anything and everything. So we just include everything right there. All right, I'm going to give you I want to do another one here for a second. What about a statement like this? X is greater than 3. How about or this time? Or x is less than 7. All right, well, let's see here. Let's go ahead and graph it over here, see what happens. X is greater than 3. X is less than 7. Now, let's take a look here. Now, if this was an and statement, we would be looking at this part right here in the middle. But it's not. It's an or statement. So what does that mean? Well, remember, we said that or is all-inclusive. Anything that's being shaded, we're going to include. Well, as I look at this, what's being shaded? Well, everything is being shaded. Okay, so I'm just going to put a number down here. Let's say I put, I don't know, 0, doesn't matter. And then I'm just going to put an arrow up here like this. And that indicates that everything's being shaded. And so what's my solution? Well, it's all real numbers, meaning everything is an answer. Okay? So those are special cases. So let's talk about solving now. Talk about solving. Okay? Well, solving compound inequalities isn't terribly difficult, okay, because you have two different types. You have and or, so let's start with the ands. How about something like this? Okay, so now you notice here we have our variable here, and in order to solve this, what we're going to do, or if you just think about it, if I take this part out, what you would do is you just subtract 2. Well, if I took this part out, what I would do is I would just subtract 2. So what I'm going to do is I'm going to just subtract 2, but I'm just going to do it from all 3 parts. So this gives me 1, x, and 5. So all values, if I'm going to put in the solution sets, I'll just go like that. Easy enough. All values of x such that x is greater than or equal to 1 and less than or equal to 5. And that's it. That's all there is to it. Let's try one more. What about this? Okay, so let's go through and solve. So I'm going to subtract 7. So I got negative 8 here. Oops, it's just less than. And now I got to divide by negative 4. Now don't forget, our dividing by a negative rule still applies. So when I divide, I get 2. I'm going to flip my sign. Flip this sign also. So I'm looking for all the numbers that are bigger than or equal to negative 1, or if we go this way, I guess, x is less than 2 and greater than or equal to 1. Put in solution sets. Okay, but what if it's an or statement? An or statement would say something like this. Remember, or statements will actually have the word or in them. And what's easy about or statements is you just solve them like two different problems. So over here on the left, I'm just going to subtract 7. Divide by 5. Now don't forget this. Write the word or. Add 2. Divide by 3. And there you go. All values of x such that x is less than or equal to -2 or x is greater than or equal to 5. And that's it for compound inequalities.